Hello everyone and welcome to the 13th lecture in the course on solar photovoltaic system design. So in the previous lecture we looked at the working of the solar cell in detail, what happens at the different depths in a particular solar cell. So today we will look at one associated phenomena in the solar cell which is not really a desirable phenomena, it is basically a lossy phenomena, and that is known as recombination. So let us go ahead and have a look at this very important aspect of a solar cell. So as we have been discussing, when there is an incident light on the solar cell, there are different photons which are impinging on the solar cell and they are getting absorbed by the solar cell. So as we understand, whenever a photon has its energy more than the band gap energy, EPH more than EG, that leads to the creation of electron hole pairs. So this particular photon which has energy more than the band gap energy, it will impinge on the material, get absorbed by the solar cell, and it will raise an electron from its valence band to the conduction band, thus creating the electron hole pair. So there is an electron which is in the conduction band which can conduct, and the vacancy which it left behind where it was previously sitting, that is the hole. So thus it creates these surplus charge carriers. However, there is something which can happen which can sort of disrupt this process. So that is the phenomena known as recombination. So due to some unwanted phenomena, the electron hole pairs may recombine before being separated apart and sent to the opposite terminals of the solar cell. So ideally what we would like to happen, if we look at the schematic of the solar cell, what we had discussed in the last class, if you can recall, you have that N plus emitter on the top and you have the P base at the bottom, and then you have a space charge region which gets formed around this PN junction, and in the space charge region there is an electric field which exists and which creates the entire magic of the solar cell. So as we discussed in the last class also, that if you have light hitting at a particular solar cell and getting absorbed at some depth, it can be absorbed in the dead layer at the top layer, or it can get absorbed in the space charge region, or one diffusion length below the space charge region, or in the very bottom of the solar cell. Different regions behave differently, but the idea is that at any location when it gets absorbed and it fulfills this criteria that the photon has energy more than the band gap energy, then it creates the electron hole pair. So there is an electron, there is a hole which is separated. So ideally what we would like to have, as we discussed earlier, that let us say if it is in this third region of the solar cell, one diffusion length between one diffusion length below the space charge region up to that depth. So this electron will be wandering here and there, and if it lands up at the edge of the space charge region, the electric field does its task and redirects it to the front surface of the solar cell, where you have these current collectors or the fingers through which the electron is collected and sent to the external circuit. So that is the desirable route which the electron should take, and similarly the hole will pass through the bottom of the solar cell. So that is the desirable thing. However, there is this unwanted phenomena or undesirable phenomena in which once you created the electron hole pair, instead of taking this path to the external circuit, what if the electron comes and sits back in this vacancy hole? So that is what is recombination. So as we understand, recombination is really an undesirable phenomena because it leads to the loss of the electron hole pair, and the photon which was absorbed, it goes waste, it is sort of going waste and becoming useless. So we do not want this recombination to happen immediately. We want that they should be separated, the electron hole should be separated, and they should be sent to the opposite ends, opposite terminals of the solar cell. So your electron should go to the front side or the negative terminal of the solar cell, and your hole should go to the bottom side or the positive terminal of the solar cell, and from there they should circulate through the external circuit and then come back and recombine. So that is the desirable thing, but in this case, as we are discussing, that if the electron hole pair are recombining before being separated apart and sent to the opposite terminals of the solar cell, that is a undesirable thing, and that is what we are going to study today in detail, why that happens. So there are two most important phenomena which come into picture in this regard, which lead to this undesirable recombination. First one is known as the imperfection recombination, and second one is known as the surface recombination. So we will look at both these phenomena one by one in detail and try to understand what exactly is happening in both these phenomena. So to begin with, let's look at the imperfection recombination. So as the name indicates, there is something of an imperfection in the solar cell which is creating this recombination. Now what is that imperfection? Let's look at it. So it occurs when the theoretically ideal crystal is impure due to foreign atoms, crystal structure errors or similar. So basically if you have an impurity in the solar cell, so ideally we don't expect any impurity in the ideal crystal. It is like a perfect crystal of silicon having no impurity. There are dopants which we are putting in the solar cell for doping the silicon to create n-type and p-type semiconductors. That is different. That is the desirable impurity. It's not really an impurity, but we call that as a dopant. So we are putting the dopant to create n-type and p-type semiconductor, and then we combine the p and n-type semiconductor together to form the p-n junction and the solar cell. However, apart from the desirable dopants, if there is some undesirable impurity, some foreign atom which is not supposed to be there, or there is some crystal structure error, there is some error in the crystal structure due to which some unwanted energy bands or energy states are created, those are the ones which create this imperfection recombination. And what happens due to this imperfection is that in this case the forbidden zone is no longer empty but has additional levels. So suppose for example, let's say you have the valence band of the semiconductor here, silicon semiconductor let's say, and then you have the conduction band. So between the valence band and conduction band there is this band gap which we indicate as Eg. So there is no energy level in between. So under default condition, when the semiconductor is sitting idle, when light is not falling on it, then all the electrons, they are present in the valence band. They are just sitting here, and once it is exposed to light, and light will come and particular photon gets absorbed, and if the photon fulfills the criteria that it has energy more than the band gap, then it will lift the electron to the conduction band. And once the electron comes here to the conduction band, it is available for conduction, contributing to the photocurrent. So that is the normal operation of a solar cell. But if you notice here, in between the valence band and conduction band, there is nothing. There is no energy state in between. So either the electron can exist in the valence band or it can go to the conduction band. There is no any other energy state in between these two bands. So that is what we are calling as the forbidden zone. So in an ideal crystal, this band gap is like a forbidden zone. So if my crystal is ideal without any impurity, without any crystal structure error, then this particular zone between the valence band and conduction band, we can call that as a forbidden zone. There is no possibility of an electron existing within those two bands. So that is the case of the ideal crystal. On the other hand, if we look at crystal which has got some imperfection, either any foreign atom or any crystal structure error, then the situation is different. Let's look at it with one example. So this sort of funny looking schematic very aptly portrays this particular concept. So again, if you see here, we have taken for example a silicon crystal, and Wv indicates the valence band. This is the valence band level where the electron is existing in its default state. Then you have the Wc, which is a higher energy level, and that is the conduction band here. So initially the electron must have existed in the valence band. That is not shown in this picture, but as we understand, by default it exists in the valence band. Then let's say some photon of light came and it raised this electron to the conduction band. So the picture shown here portrays the story after that event. So your electron has been raised to the conduction band or the higher energy level. And as we know, the band gap of silicon is this value 1.12 electron volt. So the Eg or band gap for silicon is well known to be 1.12 electron volt. We will be using this number and again. So it is always good to keep this in mind, that when we talk about silicon, then the band gap is 1.12 electron volt. So now if you see here, now there are three different scenarios given in this one figure. So first scenario is this one here, where your electron has been raised to the conduction band by absorption of a suitable energy photon. Now here, this entire band gap in between is a forbidden zone. There is no other energy state which is existing in between. So as you can see here, this electron is sort of happily standing up here at the conduction band level. It's sort of funny way of representing the electron with a human symbol. So the electron is standing here, very content and satisfied with its arms on its waist and just looking down, and he's okay, he's confident he can stay here because there is a huge band gap. There is a 1.12 electron volt difference which the electron can't really jump on its own. However, let's go to the second scenario. So that was the first scenario. For this is the ideal crystal in the first scenario. Second scenario, here there is a sulfur impurity. So there is an impurity of sulfur atom in the silicon crystal. Now as we understand, sulfur is not a desirable thing to be in a silicon crystal. So when we create the crystalline silicon solar cell, we have n type and p type semiconductors. For n type semiconductor, we do the doping with group 5th elements of the periodic table. Typical example is phosphorus. And to create a p type semiconductor, we do the doping with the 3rd group elements of the periodic table. Typical examples are boron or aluminium. So those are the dopants and they are expected to be there. But sulfur, in no way, we don't use sulfur at any time for doping silicon crystal. So this is definitely an undesirable impurity. And interestingly, what happens if you look at the sulfur atom, it has got an energy state somewhere in between the valence band and conduction band of silicon. So the energy band of sulfur is 0.94 electron volt above the valence band of the silicon crystal. So that is what is shown here. You can see the sulfur atom presents an energy band which is 0.94 electron volt above the valence band of the silicon crystal. And obviously, because the total energy band or the energy gap is 1.12 electron volt, so this sulfur energy band is just 0.18 electron volt below the conduction band of the silicon crystal. So as you can see, in this case, sulfur is presenting one possible energy state in which the electron could exist, and that is why if you see here the funny schematic on the top, the electron is looking down, it has got some temptation to go down, because there is a natural phenomena you must be aware of, that any naturally occurring particle, be it an electron or a proton or any other subatomic particle, each of these particles, they want to be in the lowest energy state possible. So if it sees a possibility of going down, there is a sulfur step available in between. Now it is thinking, so to say, it is sort of, this schematic shows that the electron is thinking, because why it is thinking, because this 0.18 electron volt it can easily jump, but after that there is a huge jump of 0.94 electron volt which might not be very feasible for the electron to make that transition. So that's why it's still in doubt, but there is a possibility. So this is just funny or a schematic way of representing it. Practically what we would say is that the probability of recombination, or the probability of the electron jumping back, probability of recombination, I can say probability of PRC. So the probability of recombination here is almost close to 0 because there is no energy state in between. The probability of recombination here is low but not 0, because the gap between the sulfur band and the valence band of silicon is quite large. So the electron can make the transition of 0.18 electron volt, come to the sulfur energy band, but from there to make this huge transition of 0.94 electron volt, it will need some excitation. It can't probably do that on its own. So that is why it is shown like there is a possibility, but it is still thinking about it, or mathematically the probability of recombination is still low. Now we come to the third case, the third scenario here, which shows an iron impurity in a silicon crystal. So as you can see here, there is an iron atom in the silicon crystal, and interestingly the energy band corresponding to iron atom is almost midway between the valence band and conduction band of silicon. So as you can see here, this iron energy band is almost midway. It is 0.55 electron volt below the conduction band and 0.57 electron volt above the valence band of silicon. So it's almost midway. Now in this case, the electron doesn't think twice, it just makes that transition, because now the energy gap which it has to travel is almost half. So it can make first the transition from the conduction band down to the iron impurity energy band, and from there again it can make another transition of a similar amount, 0.57 electron volt, and come back to the valence band. So this type of phenomena is what we call as the imperfection recombination. You have some particular impurity in the crystal, and that is providing an escape path to the electron. It can just fall back to the valence band through that particular impurity energy level. So it can be due to a foreign atom, as we just now saw, due to presence of, let's say, an iron atom in the silicon crystal. Also sometimes it can be due to some crystal structure error. So what, that's not shown in this figure, but basically crystal structure error means there is some particular error in the crystal structure, due to which there is some sort of a energy band which is created in between, midway of the, or somewhere in between of the band gap or the forbidden zone. So that energy state which is created due to the crystal structure error, that also presents the same possibility, that the electron can make the transition from the conduction band to that crystal structure error band, and from that structural error band it can again go back to the valence band. So all these types of impurities, either foreign atoms or crystal structure errors, they provide an easy escape path for the electron to recombine with the hole without going to the external circuit and without giving the usable photocurrent output. So this is an undesirable phenomena. We want to cut down on this phenomena. The recombination centers caused by the foreign atoms are also called as traps. So that is how we technically call those particular atoms. So the iron atom which we saw in the previous slide, that iron atom is basically a trap for the electron in the silicon crystal. Besides foreign atoms, also crystal errors such as empty lattice places or crystal displacements lead to the increased recombination. That also we talked about, that if you have crystal structure and there is some displacement of some particular atoms within the crystal which is creating an empty lattice place within the conduction band and valence band, then that empty lattice place also gives easy escape path for the electron to jump from the conduction band to that empty lattice place, and then from there down to the valence band. So all these are imperfection recombinations. So what to do about this? How to deal with imperfection recombination? What do you suggest? So the way to deal with it is to have utmost care for purity in the manufacturing process of the silicon solar cell. And that is why, if you might be aware, the silicon solar cell manufacturing process is very capital intensive, you can say. It demands a very high degree of precision, purity and accuracy. So usually the facilities where this type of, so if you look at the entire process of silicon solar cell creation, so first you develop the silicon ingot, and then from the silicon ingot you have the silicon wafers, and from the silicon wafers you get the solar cells, silicon solar cells, and then you assemble the solar cells together to create the solar module or the solar panel. So any such facility, if you happen to visit any of these facilities where any part of this process is being done, let's say the growth of the silicon ingot or wafer manufacturing or solar cell manufacturing happens, all those facilities are supposed to be of a very high precision and accuracy, and usually they have a space known as a clean room where the manufacturing process takes place, and you can't just walk in within that clean room with any set of clothes or footwear. You have to wear some specialized attire, suit for entering the clean room. You need to have a specialized footwear before you enter the clean room, and a very high degree of purity and cleanliness is maintained, so that there is no impurity, no dust particles, any foreign impurity should not enter the silicon crystal. So that type of high degree of precision, accuracy and cleanliness is needed for manufacturing the silicon ingot, wafers or solar cells. Then let's look at the second phenomena. The second phenomena, which again plays a key role in recombination, is known as the surface recombination. So if we look at the definition for this, first we need to understand what is a crystal. So a crystal surface is also a disturbance of the ideal infinitely extended crystal. So if you talk about a crystal, basically let's say a silicon crystal, so theoretically speaking, or an ideal crystal is infinitely extended. Now we understand there is nothing like infinite extension of any particular material, but this is still the theoretical concept. So let's look at it, what it looks like. So as we understand, we know that silicon has 4 atoms in its valence band, and then in the crystal structure there are other silicon atoms, adjoining atoms, which each one of them has 4 electrons in the valence band, and these electrons are contributed to form the bonds with the other silicon atoms. So each silicon atom contributes one of its electrons to 4 of the neighboring silicon atoms to create the bonds with the neighboring atoms. So something like that. So you can keep on drawing like this, it can be infinitely extended. So each silicon atom is having 4 electrons in the valence band, and there are adjoining 4 atoms of silicon, and it is contributing 1 electron each to each of the adjoining atoms to form the 4 bonds around its. So that's the type of thing, it can, we can go on drawing this infinitely, there is no end to this. You can keep on drawing infinitely like that, on all sides, and then these guys also will have something like that. So you can keep on drawing infinitely, and that is the idea of a silicon crystal, right, something like that. So that is why we are saying here that a crystal surface is a disturbance of the ideal infinitely extended crystal. So the ideal crystal is infinitely extended, it will go on, you can go on creating this type of a diagram infinitely, so 4 bonds in each direction, and then adjoining atom again has 4 bonds in each direction, then the above atom again has 4 bonds in each direction, the lower atoms again have 4 bonds in each direction. So it can go on being extended infinitely. So that is the theoretical ideal crystal, which is infinitely extended. But as we just now said, there is nothing like, practically we cannot have a infinitely extended crystal, it's not really possible. So practically there will be some surface, there will be some boundary for the crystal. Now let's say this is the crystal boundary, suppose. So these bonds which we just now drew on the upper side, they will not exist, right? So these bonds will go away. So wherever there is a crystal boundary, those atoms which are on the crystal surface, they will have some open bonds, they will have some particular open lattice spaces. So the electrons of the outer atoms do not find bonding partners and remain as open bonds, and that leads to undesired surface recombinations. So these lattice places provide the opportunity for recombination. So any crystal will have some surfaces, and those surfaces form the sort of disturbance of the ideal infinitely extended crystal, and the outer atoms which are at the surface of the crystal, they have open bonds, and those actually lead to these undesired surface recombinations. Now what to do with it, what is the possibility, because obviously there will always be this some surface would be there in the silicon crystal. So what do you suggest, how to deal with this? So to deal with this, what we need to do is something given here. So from this consideration, it becomes clear that a crystal used for solar cells should be single crystalline as far as possible and of a high degree of purity. So now what I would like to do, because there is surface recombination happening, ideally what I would like to do is that within a given solar cell, I would like to have the minimum possible number of the surfaces. So if I have a solar cell like that, I would like that this entire solar cell is just one single crystal. So there are just 4 boundaries. We are looking at a 2D figure, that's why we are calling 4. If you look at a 3D figure, that would be better. So you can have different faces like that. So there is one surface here, second one here, third one here, fourth is this one, fifth is the top one, and sixth is the bottom one. So there are these 6 surfaces for a 3D, let's say a cubical solar cell. So these 6 surfaces will definitely be there. There is no way to reduce it more than that. But we would not like to have any other crystal surface or boundary within the solar cell. So only the external boundary, external surfaces of the solar cell should be the surfaces. Within that boundary of those surfaces, the entire solar cell should be one single crystal. So this is what we call as a, so if this entire solar cell is just one crystal, we call this as a single crystalline, also known as the monocrystalline. You might have heard of that name more popularly. So this is a single crystalline or monocrystalline silicon solar cell, and this has relatively higher degree of efficiency because surface recombinations are at their minimum. I mean, at those 6 surfaces recombination will happen, but there is no way we can reduce the surfaces to any number less than 6 for a cubical surface. On the other hand, there is still a possibility, let us say there is some other crystal where again we assume a cubical shape for my solar cell, something like that. But within the cubical shape itself, there are more surfaces. So there is one crystal here, another crystal going like that, third crystal here, some fourth crystal here, like that. So if I create a solar cell, if I manufacture a solar cell like that, within the solar cell, there are different crystals. So you have more crystal boundaries. So 6 crystal boundaries we already identified on the edges. Then there is 7th one here, 8th one here, 9th one, 10th one, 11th one, like that. So this has got many more crystal surfaces. So these are different crystals within the boundaries separate out the different crystals. So this type of a solar cell is what we call as a multi-crystalline solar cell. Multi-crystalline, or another name is polycrystalline. Both mean the same thing, more than one crystal in a solar cell. So if you have a multi-crystalline or polycrystalline silicon solar cell, this will usually have lower efficiency. Why? Because the surface recombination is higher here. So that is always there. So we need to be careful about how we are creating the solar cell in terms of the degree of purity and also how many crystals are there within the solar cell. So always monocrystalline or single crystalline solar cells are more efficient. They will have slightly higher efficiency, whereas this one, where you don't do a very careful manufacturing process, and when you grow the silicon ingot and then from there you cut the wafers and create the solar cells from the wafers, then the sort of level of precision or accuracy is not maintained to a very high degree, and due to that a single solar cell might be composed of different crystals. So in that scenario the efficiency is lowered, and this type of solar cells are known as the multi-crystalline or polycrystalline solar cells. The trade-off is that now this single crystalline or monocrystalline solar cell, this will be little more expensive also, so the cost is also somewhat higher. This is less costly because the manufacturing process is not so rigorous. The checks and balances in the manufacturing process are lesser. So this is less costly, this is more costly. The monocrystalline is having a higher cost but also gives a higher efficiency. The multicrystalline has lesser cost but also gives a lesser efficiency. And the trade-off we need to work out. And interestingly, you will see now the solar cell prices have come down very drastically. In our first lecture, we looked at the pattern of drop of solar cell prices, which has happened in a very drastic manner over the last 4 decades, and especially in the last couple of decades, very drastically. So now, at the current level of technology, if you do the techno-economic analysis, the single crystalline or monocrystalline solar cells, they actually win over, because the cost is slightly higher, but the overall higher efficiency over a 25-year lifespan gives you much more higher electricity return, energy return, and gives you more monetary benefit. So with the present state of art of technology, the single crystalline or monocrystalline solar cell are more techno-economically viable. However, if you look at the technology, let's say somewhere 8-10 years back, maybe around 2015, 2017, at that point of time, multi-crystalline used to make more sense, because that time the cost of solar cells was prohibitively, I mean, not so much, but still quite high as compared to the present times a decade back. So due to that higher cost differential, the Technoeconomic used to work in favor of the multi-crystalline solar cells. So if you look at the older power plants, let's say power plants established before 2017 or 2018, around that period, before that, multi-crystalline used to be the choice for the Technoeconomic reasons. However, the recent plants, let's say 2020, 21 onwards, those plants, they go for monocrystalline solar cells because the cost differential is very low, but the higher efficiency has a much more benefit over the entire lifetime of the solar panel and the solar plant. So this summarizes our discussion on the types of recombination. We looked at the imperfection recombination created due to the foreign atoms in the solar cell or due to the crystal errors, lattice space errors in the solar cell. On the other hand, we looked at the surface recombination, which is happening mainly at the surface of the silicon crystal. Now, whatever type of recombination is there, any imperfection recombination or surface recombination, what effectively it does is that it reduces the lifespan of the charge carriers within the solar cell. Because as we discussed in the opening of this lecture, that undesirable recombination means you created the electron hole pair, they split out and then they again recombine. Ideally, they should have been driven in the different directions, went to different terminals and went to the external circuit. That would have been the ideal case. But if recombination is higher, undesirable recombination is there, then you split them apart and they again recombine. So effectively, if the recombination is higher in a solar cell, then the lifetime of the charge carriers in the solar cell will be small, and the distance they can travel within the solar cell will be also small on an average. So to quantify this concept, there are two things which are used. One is the carrier lifetime, another is the diffusion length. So let's quickly look at that as well before we end the lecture today. So carrier lifetime Tn defines how long a generated electron exists on average until it recombines again. So different electrons will have different destiny. Some will go to the external circuit, some will recombine before going to the external circuit. But overall, on an average, if we look at the average carrier lifetime, it gives us a sense of how much is the extent of recombination in the solar cell and whether it is acceptable or not. So depending on the quality of the silicon and the doping concentrations, it lies in the range from milliseconds down to microseconds. So that is the range for which your charge carrier exists within the silicon solar cell, somewhere from milliseconds to microseconds. Apart from the carrier lifetime, there is another concept which is also used, which is known as the diffusion length. Now this might be sounding known to you earlier also, because in the last class we discussed about when we were talking about the different depths of the solar cell, we looked at what happens one diffusion length below the space charge region. So diffusion length is also quite popular, and it describes the distance a generated electron travels in the semiconductor until it recombines again. So both these parameters, carrier lifetime and the diffusion length, they represent the same phenomena, that what is the extent of recombination happening in the solar cell. If recombination is higher, then the electron will have a lesser diffusion length and also lesser carrier lifetime. It will recombine quickly. If the recombination is lesser in the solar cell, then the diffusion length will be more, it can diffuse to a longer distance, and also it will exist for longer duration of time, or carrier lifetime will also be more. So both of these are interconnected by this formula. Diffusion length Ln is equal to under root of dn into Tn, where your dn is the diffusion constant of the electron, and this is typically around 35 centimeters square per second for crystalline silicon. So let's do a quick numerical example to understand this concept in little more detail. So suppose if you have a crystalline silicon solar cell, and there are two cases given here. If it's in one case we are saying the diffusion length is 50 micrometer, in second case we are saying the diffusion length is 500 micrometer. So these are usually the maximum and minimum values. Typically in a crystalline silicon solar cell, the diffusion length will change depending upon the impurity levels and the doping levels. However, these are the typical values. It will be at least 50 micrometer or at most up to 500 micrometer, in that range. So let's solve this numerical. Let's find out what is the carrier lifetime for an electron in this crystalline silicon solar cell. So as we just now looked at it, Ln is equal to dn into Tn raised to power 0.5. Or in other words, we can say Ln square is equal to dn into Tn, and therefore your carrier lifetime Tn is nothing but Ln square by dn. Now in the first case, we are saying that our Ln or diffusion length is 50 micrometer and dn has been given as 35 centimeter square per second. So it's always easier if we convert it to the same units. So ln also let's convert to centimeters. So this will be 50 into 10 to power minus 4 centimeter, and therefore I can say that my Tn would be 50 into 10 to power minus 4 whole squared. This is in centimeter square now, and divided by dn is 35 centimeter square per second, and as you can see dimensionally also centimeter square and centimeter square gets cancelled and you get the time in seconds. And if you solve it out, you will get this as 7.14 into 10 to power minus 7 seconds, or we can say 0.714 microseconds. So in this crystal, if the diffusion length is only 50 micrometer, means your electron is existing on an average only for less than a microsecond, 0.714 microsecond, and in that much time it can travel on an average this much length, 50 micrometer. On the other hand, if you look at the second example here, so here the ln is given as 500 micrometer, or we can write it as 500 into 10 to power minus 4 centimeter, and therefore my Tn comes out to be 500 into 10 to power minus 4 whole squared divided by dn is 35, and if I solve it out, so we get this as 7.14 into 10 to power minus 5 seconds, or equivalently we can say 71.4 microsecond. So that is the typical range. Your electron on an average in a crystalline silicon solar cell, it travels somewhere between 50 micrometer to 500 micrometer depending upon the doping level, impurity level of the silicon and several other factors. So it travels somewhere between 50 to 500 micrometer and exists for somewhere between 0.7 microsecond to around 71 microsecond in that particular range. So this is a little bit about the recombination phenomena in the solar cell, and we looked at the two types of recombination phenomena and what are the drawbacks of those phenomena and how to deal with those phenomena. We looked at the conceptual understanding of those things, and then we looked at this numerical example to understand how recombination impacts the carrier lifetime and the diffusion length in a solar cell. So that is it for today. In the next lecture, we will be discussing about another very interesting phenomena in solar cell, which is the phenomena of absorption of light in the solar cell. How does light behave inside a solar cell? How does it get absorbed? And some of the related aspects related to that concept. Thank you for joining us today.